Good morning, good afternoon, and good evening, everyone. My name is Eric Mayo, and I'll be helping moderate today's webinar on JuliaHub, introducing single-click scaling and cluster deployment in the cloud. Thank you all for joining us to learn about some exciting additions to JuliaHub. JuliaHub is an entry point for all things Julia. Explore the ecosystem, build packages, and now easily and robustly run code in the cloud on big machines and on-demand clusters. With a single click, you can speed up existing analyses and leverage supercomputers in the cloud for rapid deployment and iteration. We'd like today's session to be interactive, so please write your questions in the chat. We will either address them on the fly or address questions individually following the demonstration. With that said, it's my pleasure to introduce today's presenter for our JuliaHub webinar, Dr. Matt Bauman. Dr. Bauman is a 7-year contributor to the Julia language, has been with Julia Computing for 4+ years, and wears many hats within the organization. Some of his credits include the creator of our Learning Center, Julia Academy. Matt is a Julia class instructor, a pre-sales engineer, technical support engineer, and software developer, having made over 500 contributions to the Julia language within the last year alone. Please welcome Dr. Matt Bauman.
Thanks so much, Eric, and great to see all of you here today. I hope you'll enjoy this. I had a lot of fun putting this webinar together, so hopefully you'll have fun following along with this story. We've been working very hard at Julia Computing to make it as easy as possible to deploy your code and scale it up to the cloud. And this takes form across lots of domains. I'm just going to focus on a couple for the purposes of this demonstration. One is just the de facto hello world of a machine learning task. That's handwriting recognition, right? This is kind of where folks start often when they start talking about machine learning and artificial intelligence, is how to do a task like this, a detection task where you want to train a neural network and recognize handwritten digits. Of course, this is just a simple demo, and it extends to large classes of machine learning toolkits and pipelines, but is a tractable problem that allows us to really dig in and understand what's going on. Julia is also built for all sorts of great domains, and one such domain is the life sciences with the Pumas package. There's lots and lots and lots of great tooling built around this that's entirely in Julia for doing scientific machine learning in the context of pharmaceuticals. And this is a great package for using your Julia code and deploying it and getting things going. Another example is AlphaZero. And AlphaZero is this kind of cool intersection of machine learning and for search and learning, where AlphaZero is the agent that was trained to play Go against a human player and beat one of the best, if not the best, human player in the world back in 2016. It's a really impressive bit of machine learning architecture where the search space for the game of Go is just intractably large. And so you use a combination of machine learning with neural networks, understanding the game, as well as search to kind of make that search space tractable. And it's a task that's challenging because it requires a ton of compute. In fact, all of these tasks require lots of compute. And Julia makes it as easy as possible to get things going. But often there's a barrier in getting things, moving things to the scale that you need them to. And so that's what we've been working on. With AlphaZero, it's gone a step farther with the Julia language to make it as simple and as expressive as possible. And this is work done by Jonathan Laurent, a PhD candidate at the Carnegie Mellon University. And he's worked very hard to make this as simple as possible. And because Julia is a high-level language, you can play with it. You can understand it. It's tractable at that point. It's just 2,000 lines of pure Julia code. At the same time, it's fast. You're able to train this in a reasonable amount of time, assuming you have GPUs available to you, because this is geared towards GPU compute. It's extensible, allowing you to plug in new learning frameworks and new games. It's also built to scale. And that's what I want to talk about today, is how all of these tasks, from life sciences to finance to machine learning to the most advanced machine learning algorithm there is, they're all requiring more compute than you have on your laptop today. They all need the ability to scale out and deploy quickly and easily. And fortunately, Julia itself is built for parallelism. And in fact, we have 3 really awesome modes of parallelism built into the language, either through the language itself, its standard libraries, or really, really solid packages. So on the left there is this is the icon for the Julia GPU organization. The little GPU card here that represents all the great work that's gone into making Julia as easy as possible to run on GPUs. In fact, you can write in almost CUDA code entirely in Julia without needing to dive into CUDA, just leaning on broadcast as well as some of the CUDA intrinsics with the new and revamped CUDA package. It's a really awesome way to speed up your code. There's multi-threading built into the language itself. And this is, as of Julia 1.5, now on stable footing. It's no longer experimental status, and is a really great way of speeding up your code on a single computer. And of course, all of these things work extraordinarily well with the distributed compute library, where you can go into clusters or even supercomputers with distributed compute, connecting lots of machines together and getting this going. Of course, not all of us have a supercomputer at our fingertips. You know, sitting next to me in my apartment here, I don't have a supercomputer, but I do have access to one in the cloud. And so we want to make that as easy as possible. Just to put a bit of a finer point on this, you know, the most basic of machine learning tasks, they require GPUs to do your training in a reasonable amount of time. The life sciences kinds of simulations and things like that can, you know, be deployed across many computers and on clusters. And in fact, within those clusters, you can indeed use GPU processing as well. But then AlphaZero uses all 3 together. It uses many threads on a single computer to batch up work and send it to a GPU. And then it connects many computers together to turn away on the problem all at once. And so we've taken great pains to expose all 3 of these mechanisms on JuliaHub itself. And hopefully you are all familiar with JuliaHub. If you're not, it's a great entry point for the entire ecosystem of Julia itself. It's a really wonderful place to go and find, you know, all the things that you need to find. In fact, at this point, I think I will just dive out of the presentation and just go to the web browser and take a look at what JuliaHub looks like. And we can look and see exactly how this looks, what's going on here, and how you can use this. So without even logging in, I have this view of the ecosystem at a glance, easily able to see and explore all the awesome things that are happening within Julia, from scientific machine learning, which is kind of the theme of JuliaCon 2020. You know, you can take a look at all the great packages here. It's many of the other packages, from, you know, linear algebra, bioinformatics, to even web programming. There's a lot of new work going on here. So this is kind of how you can explore the ecosystem, find things. And in fact, you can go a little bit farther and search through documentation, gain familiarity. Even if you don't know where a particular function is, well, just search for it. And this searches across the entire ecosystem. And so you can take a look and see, you know, where are neural networks, you know, found within the ecosystem. It's really fast, right? And you can see all the different sorts of neural network libraries that we have in Julia. But now the cool thing here is I can log in. And by logging in, I gain access to a whole host of other capabilities. Oh man, lost my authentication here, just one second. you gain access to a whole host of other capabilities and the ability in particular to launch code on the cloud. Give me 1 second here. Okay, so we have this ability to now run code in the cloud. And you can see that we're kicking everybody off with $25 of free compute credits in the cloud just to get you started. This is not publicly accessible quite yet. If you go to the homepage, you can actually get notified, and we're going to start rolling this out next week. But let's look and see how this works, how you can get things running within JuliaHub. The easiest way to do this is actually from Visual Studio or Julia Pro. And what I have here is I am right now connected to JuliaHub within my Visual Studio IDE right away. And so, what I want to do is I want to train that handwriting recognition task. I want to train that to recognize handwriting, right? I want to train this. And in fact, we have that task. It is available. FluxML is our machine learning framework. You can go to fluxml.ai to take a look at it. And in fact, there's some really cool experiments, including this MNIST classifier. And the code is available here for you right online. It's part of what we call the model zoo, all the different models that are available to you. And this is an example of one such model. So this is entirely open source. You can download it and get it going. In fact, that's what I did here in my local environment. I downloaded this. Here's the model definition itself. For those of you who are familiar with machine learning, this shouldn't be too complicated here. Let's go to our model definition. Where is it? Here it is. So here's our function that builds our model, and it's just a chain of convolutions ending with a dense neural network. And so this is a very standard Flux machine learning model, but I want to train this, right? Simply defining the model doesn't do me any good. I need to train it against data to get it to work. And if I were to do this locally on my laptop, it'd take about 2 hours to train it for the amount of time that I need to get the accuracy that I'm after. And that's because my laptop doesn't have a GPU. I don't have access to a GPU on my laptop, which means that I'm constrained by my CPU performance, which is decent, but the GPU is geared for matrix multiplications, which underlie the heart of this machine learning operation and can do this extraordinarily fast. And so this training function here actually is built to work both on CPUs and GPUs. In fact, it's as easy as saying, using CUDA. And then with that, if I don't have it, it's fine, it just runs on my CPU. If I do have it, well, then I'll get this notification that, hey, we have CUDA available to us. And then all I need to do is, for example, let me grab GPU. I just move my data onto the GPU. And this is how you do that. You just simply call a function to say GPU my test set, GPU my model, and if I have a GPU available, it'll move the data over there for compute over there, and it'll batch it together. It does this extraordinarily efficiently. But like I said, I don't have this available to me on my local laptop. I do have it available to me in the cloud, though, and that's what JuliaHub now provides. I have my Visual Studio connected to JuliaHub. You can see I'm authenticated, and it knows that I want to run this train file, which simply includes my model, trains it and tests it, figures out the accuracy, prints out how long it takes and such. And I can say, hey, let's deploy this in the cloud. And I can say, I just want to use one machine or one node as the terminology here that has a GPU attached to it and 12 gigabytes of memory per GPU set up here. I can even set a a time limit, but you can get a sense of, what the cost is here. It's only $1.40 per hour to spin up a GPU machine like this. So it's really quite reasonable to get this going. And the speed gains here are significant. I can start this job here and it'll connect to the cluster, send all the things that I need to in order to do it. It knows that I'm working within this directory and file, and this is the main entry point for my file. It knows that I'm including some other source here. I'm including this model, and then it also knows, because I have this set up within an environment that has a project and manifest, it knows all the packages that I need to use. Not only that, it knows all the exact versions and all the dependencies and things like that. So it can, deploy exactly what I want and exactly what runs locally to the cloud. And so I just hit deploy here. You can actually see this here. I have a new submitted job that I just submitted a minute ago, or not even, and now it's running. And I can actually watch the live logs come in here as it boots up this machine in the cloud, connects to it. You can see here it's starting this worker, getting things all ready to go. And instead of waiting, this will take about 10 minutes to boot up, run the code, complete, train it, and get things going. Instead of waiting for that to happen, I can just pull up a run that I did an hour ago here. You can see that I ran this exact same thing an hour ago. I can pull up the logs on this as well, and you can see here that I finished running my code successfully with an accuracy of 0.9929, or 99.3% accuracy against the test data set. And you can go in here and look at all the info, all the logs that I have. I have this set up to log all the accuracy, to give me info messages, things like that, so I can see exactly what's going on. And in fact, I can search through these log messages to just see, how long does something take, or, find, exactly what I'm looking for within the logs. So this is really easy to look into and inspect and understand. Now, what's cool is that I also have this set up to, give me results. And the results here are the trains model, the trains, MNIST model saved as a BSON object here. And so I can save this into my local directory here. I'll save it. I'll replace what I've been working with. And this is my new model. Now, that's great and all, but really what I want to do is I want to introspect this model, gain an understanding of how that works. And to do that, well, let's just launch a Pluto notebook. Let's get a sense of, what is happening within this model. So this Pluto notebook, all it's doing is it's, including my model. It's including exactly what I need here. Let's hide these guys. In fact, you can make this into a nice dashboard. But you have here, this is, we're loading our data. I can zoom in just a little bit to make this a little bit clear. Just loading our data from that file that we just downloaded and loading it into the model that we've defined. So then, now that I have this set up, I can incrementally just kind of inspect this and play with it directly in an interactive environment. And so you can see here, this bar graph here is giving me the output of the model that I trained in the cloud in 10 minutes, got it going, got things up and running. And you can see here that it's a lot of fun just to kind of see, you can see just, can you pull it? Is this going to be a 2 or maybe a 3? Nope, it's going to be a 2. There's just a lot of fun that you can have as you play with this and kind of see, how you can fool the neural network, how good it is. And this is the kind of thing that you can do just directly within JuliaHub. And it's entirely enabled because we have access to that fast GPU. And so I was able to put this demo together in just 2 hours yesterday, from scratch with nothing going, grabbed that sample code, deployed it on the cloud, got this, little interactive GUI going. It's a lot of fun. It's great. So we can go back to JuliaHub here. And you can go to this Run Code tab, and you can see all of my previous runs here. And in fact, on the web, I also have access to this nice details button where you can see exactly, how good I did, the outputs, the number of epochs I ran for, the total amount of time that it took, and perhaps importantly, the total cost. So this, because it was just 10 seconds of one of the cheaper GPU machines, it took less than a quarter to run here. And so this is just a really, really cool way of getting your data out, understanding this. And then we can actually click on multiple runs. So I have 2 runs here, one from yesterday, one from this morning. I can click on them and compare their outputs. You can see, these 2 runs had slightly different performance. This one that I ran yesterday had slightly better accuracy on the test set. I could, download its results file as well, contrast and compare how these 2 neural networks did. But it's really easy to play with and understand.
Hey, Matt?
So that is,
Okay,
yes, go ahead.
We have a quick question from Florian.
Can I
He's
ask
asking
you?
about Pluto.
Yes.
Yeah. So the
I don't know if
Pluto
you have the chat open,
example, this is actually running locally on my computer here. I just have a Pluto notebook up and running. So what I have locally is I've locally downloaded that, where'd that block go? I've locally downloaded this BSON file, and I load it locally to introspect locally here.
Okay.
And so, yeah, this is, I just have a pluto.jl notebook server running in another process that I have connected within the same environment. And then, yeah, the Canvas code here is all right here. It's just simple JavaScript Canvas code that grabs out and binds the data to whatever I draw in here. And then the bar graph here is just running the trained model against the data that I have. And it just takes a little bit of pre-processing. This is just kind of a bit of a mess of my work here, but it just pre-processes it and does a bar graph of the output. So that's how this is working. And it's just a really simple notebook that I didn't spend too much time on, but gives me the ability to introspect this and play with it. Yeah, so that's what it looks like to, from end to end. We can also do this with more complicated examples. And so this exact same framework works, so this is what I showed you here. This is the training of the model. You can see a little bit more details on exactly how this works. But you can set up a simple JSON struct here that shows me the accuracy, the number of epochs, and the amount of time that it took. And then I just say, hey, here's the results file that I want to upload. And it's just whatever the save path was for my model. And so that's exactly how this works. So I can go into a slightly different example here. Let's go to one from Pumas. This is a similar idea. And again, the same concept works here, right? I have this complicated script that takes a long time to run and parallelizes across a number of subjects. And so here I can choose exactly how many subjects I want. I can debug this locally, just to say, hey, let's see how this works with just one subject, for example. And I have a number of iterations. This is just doing a large simulation, a large scale simulation across lots of data and trying to estimate a 56 parameter drug model that's actually an active target here. And we're collaborating with a big pharmaceutical company to work with this active drug target. And we can play with this locally, right? I can play with it locally in my VS Code environment, have all the great interface that I want here. But then when time comes to scale up, well, I just change this number, right? I just change the number of subjects that I want. I pull up my JuliaHub pane here. It'll connect to JuliaHub.com, and then I can scale out, right? And simply say, hey, let's, once this connects up, we'll be able to say, let's use this current editor as my file. You know, say we want 8 core machines. This isn't a GPU enabled task, so I won't use GPU machines for this, which makes it a little bit more affordable. And it means that I can scale out to lots of nodes here. And this is a very parallelizable task. The back end here is just running off of PMAP from the built-in distributed standard library. JuliaHub takes care of spinning up all these nodes, making sure that all the dependencies are in the right place, making sure that all the workers are in the right place, and connecting that distributed library for us. That way, all it takes is just simply, hey, let's PMAP this subject builder and get this and deploy it across here. And so I can easily build up. So if I have 10 machines, each with 8 cores, and I have a Julia process per core, this is 80 workers here that is costing me 13 bucks an hour. And really easy to start and deploy. And again, just like last time, you just single click here and can deploy this. In the real application here, this would take upwards of a day on a single computer to complete, but by parallelizing it out, you're able to get this task done within an hour or two. And so this is just huge savings. And with large, very parallelizable tasks like this, once you move to the cloud, it doesn't really matter how wide you scale out, as long as it's parallelizable. Because the cost to run 10 nodes for 1 hour is the same as running 1 node for 10 hours. This is one of the beautiful things about having a supercomputer in the cloud at your fingertips is that your cost now is entirely based upon the compute that you use, and it doesn't matter how many nodes you spin up. So yes, when I showed the dollar cost of the first example, it was just 25 cents because, so that was using a GPU machine here that was, $1.40 an hour, but it only took me 10 minutes to complete. And so it was just a quarter for my cost. And we take care of, all of the AWS shenanigans for you and make this as simple as possible. So this is how this works in general. For this particular task, the results file is just a simple CSV that, again, I can download, work with, introspect, and use very, very easily. Now, there's another way of deploying applications in the cloud, and that is if I go back to JuliaHub here, I also have access to this Applications tab. And I can go in here and add an application. And I can say, hey, let's add github.com, Jonathan, I think that's how you spell his name, alpha0.jl. You can add this, oh, shucks. I think I might need to, oh, I have a misspelling here somehow. I also have it on my local GitHub. So you can add these applications. And all this means is that this package happens to have a bin/main script in it that simply says this is the main entry point. And with that script, I can say, hey, let's run this in the cloud. It'll automatically set up a job submission pane for me here that has the project manifest all set up for me. I can play around with some additional parameters, potentially change the settings here, but this is nice if you have a baked application that is ready to go and folks can just run it with their own, own analyses. You can even choose to run off a particular branch if you're doing development work. So I could say, hey, let's run off this particular branch. It automatically figures out what you need to do. And again, this is a GPU process that actually makes good use of the more expensive GPU machines that are using these have a V100 Tesla GPU card in them. And so it's a very beefy machine, and it's expensive, but you get that cost back in the compute time because it's a more capable machine. And this is a task, like I had said, that is scaled up across multiple threads, across GPU, across multiple nodes. And so just like before, I can start this job up with 10 GPU machines all connecting together and hit start, and it will kick off this job, get things going for me very, very easily. So a question just kind of on these sliders and how they work. You can kind of see it online here with this CPU task. You know, this top section here is saying, you know, how do we want each machine to look like? And the bottom section is the number of machines that we want. And so I can say how much memory I want per core, how many cores I want in each node. And then I can choose what kind of execution model I want. I can either say, hey, on this machine, I want there to be 8 Julia processes, each of which, you know, is single threaded, or I can use multiple threads. So I could have a single process with 8 threads instead. So this is exactly how this works. Yeah. So I am going to jump over, and we can then look at what it looks like to deploy, or like to work with the results from AlphaZero. And you know, the way that looks is I can jump over to let's see, do this. There we go. I can jump over to VS Code, just like before, download my results. You know, I have this pane, I can download the results. I can then untar them, unzip them. This particular, the way AlphaZero is set up, is it has a lot of results files that are all set and ready to go. And I just zip them all together or put them all into a tarball. And you can see that there's lots of cool things within this results package. And it's been extracted out into the sessions folder where you can look and see, you know, some of its plots that it's generated as part of its, you know, runtime, as part of its compute. And so here you can see how many games did it win. And this is AlphaZero training itself for Connect 4. So it's a simpler game than Go, but it's more tractable. And had I done this locally with a GPU, if I had a GPU on my machine, it'd take a day. Instead, this took me about an hour and a half to complete on JuliaHub to spin this up. So I can load this. And then the cool thing about this is, of course, it's a game. I can play against the computer that I just trained in the cloud. And so if I make my my terminal a bit bigger here, you can, you know, drop your Connect 4 piece in. You have a little representation of the game board there, and it tells me exactly what the computer thinks is the best move. Of course, Connect 4 is a solved game, so it makes it easy to understand, and that's part of the goal of AlphaZero.jl is understandability. But this is really cool, right? You can, within an hour or two, have this task trained, ready to go. And you know, make this happen. So you can also then change some parameters, right? Change the parameters again, and then resubmit the job. So I could change, for example, the number of blocks, and submit my job again directly from the VS Code here. And you can see, you know, again, there's a cost estimate. It's a more expensive job because it's using a lot of compute. But again, the savings here are just really impressive. Now, it's kind of a fun little last sneak peek at what we're doing. This portion of the VS Code here was actually running in the browser. And so coming soon is going to be the ability to spin up Julia IDEs and Julia processes entirely in the browser, entirely on JuliaHub. So that way you have just a one-stop shop for everything. So you can see exactly how this works. But you can see here that this was actually running in Chrome to do this. This is VS Code in Google Chrome, running on a remote server. In short time, this will actually be running in JuliaHub itself. And so that's a sneak peek of where we're going. We're not seeing this as the end state. We're seeing this as, you know, a continued iteration and continued support for this. But this is how, you know, we see JuliaHub, and I think it's a lot of promise here. So, you know, as I started working with this, I've kind of changed the way I think about my computer. It's almost like a master node for a cluster now, because it's so easy and so capable to just hit submit and get things going. So as a final note here, JuliaHub itself is available for enterprise use through JuliaHub Enterprise. We can set this up with private packages for your team. So that way, not only do you get the great open source package exploration, but you also have that exact same experience with your private packages, including documentation, building, renderings, hosting, search through it all. And then the availability to deploy those local packages that you're working into your own AWS account or your own subnet, and get this, you know, spun up as quickly as possible. And that means that it can work within your own secure environment, right? Your own secure AWS networked environment. We can actually even install this within air-gapped environments, connecting to some on-prem clusters as well. And so that's available. And of course, we have the governance and security that you need to feel safe and secure in your usage of both open source components as well as support. So sign up and get early access. We're launching this to folks that sign up and request early access next week. That'll include, you know, the local VS Code connection, so a local JuliaHub plugin that you can connect to JuliaHub and submit your jobs directly from your computer onto the cloud. Also includes the ability to launch tasks directly from the website itself, right? That running cloud tab that I demonstrated, and the easy way of seeing your results, understanding them, downloading them, and working with them. That's all, you know, we have that all working, and we're ready to start onboarding early adopters beginning next week. So again, encourage you to follow this link or directly on juliahub.com. There's that get notified banner. Just say, hey, get notified. And we're wanting you all to try this. And so we're launching with, you know, $25 of compute for everybody to play with and understand. And you can see that can actually get you a long ways, right? If you have simple GPU jobs, you can get a lot done within $25. So lots of fun to play with here. Please sign up and get that going. And then, of course, coming soon is going to be the ability to actually spin up the IDE within the web browser itself. So you don't even need to download anything locally on your computer. And that's, you know, one of our next features, the advanced capabilities that, you know, we want to continue iterating here, continuing improving this. And so that's part of why we have the early adopter program here. So with that, I'm happy to take questions. I see there's one here about, you know, how does online tasks work? So I have a physical application with a Raspberry Pi, and you want to kick off heavyweight calculations and just have access to the internet. That's exactly what this is. And another one of those next steps early on our roadmap is a public API. So, you know, that VS Code plugin, the website, they're using an API to connect to JuliaHub and spin up new jobs and such. And so we're going to make that API public. So that way your embedded application can actually, you know, take its work or whatever, you know, build up a task to submit that job automatically for you, and the ability to do that. So yes, that is early on the roadmap as well, an API that allows you to, for programmatic usage, where you don't need to use a mouse to click that start job button. Any other questions here? I hope this has been helpful to gain an understanding of exactly how JuliaHub is going to work and how we're seeing this. And I really hope that all of you sign up so that way we can start getting you, start getting more testers. We want to make this as robust as possible. And so, that's the goal here. Yeah, so, the idea is the way that I've been working with JuliaHub and the way that I've been iteratively testing my own code is that I work locally with a small subset of my data. And so, for example, when I go over to VS Code here and I have this, large pharmaceutical model, well, I can just, make the number of steps very small, make the number of subjects very small. And now this runs in almost no time at all on my laptop, right? It's very easy to do this, very easy to scale this job down. Not all jobs are amenable to this, but this is how I've been working with, and it works great to do this sort of thing. You just make the set work. Now, the challenge there is with GPU programming, right? And as you saw here with this training program here that I downloaded, it was indeed already pre-baked, right? I downloaded this model. It already had everything set up to move things onto the GPU. Now, I could still run this locally, right? And I could, and this works locally if I don't have a GPU attached. It's just these GPU calls become no ops. They just don't do anything at all. And so I can still develop this locally. Now, there is that challenge with the GPU in that, this may not work, right? If suddenly you move to the GPU and you don't know what you're doing, then you're a little blind. And you can, submit your jobs, get things going, and play with them, see what's going on, and you can work with them easily here. But that leaves some things to be desired. And so that's why we want to get that spinning up the IDE in the cloud working. So that way you can spin up a machine that has a GPU attached to it, work with it within your web browser, and then you have local access, essentially. It feels like local access to the GPU, and you can do interactive debugging at that point. And so that's why that's early on our roadmap, is particularly targeting that GPU that GPU case. So the cost of that will be a persistent compute model, and so it'll be the same, dollars per hour kind of thing. At least that's what we're imagining, right? This is the same sort of compute. You're using that, and so you just have to remember to spin it up and spin it down. Again, right? For a GPU, we're talking for a single node, you're talking $2 an hour. Is what this, or $3 an hour, I guess, if you round up. Or sorry, looking at the wrong number. $1.40 an hour, and so it's pretty reasonable, pretty tractable. You can do your debugging in a day for under $10 for a whole day's worth of access, and far more reasonable than buying your own GPU machine. At least if you have limited resources, it's an easy way to scale up and get going and start working with it. So yeah, this is about what we're going to see here.
I don't know if you missed the question from Abhinav about talking a little bit more about the API. Is that something you can possibly address?
Yeah, I mean, it's just going to be essentially the same sort of idea here, right? Where you have a script that you want to submit to the cloud, and the API will guide you through exactly, what the cluster configuration is, how to submit a job. And in fact, if I go here to the, you can actually get a little bit of a sense of, what's happening here just by looking at the, the JuliaHub logging messages within VS Code here. So you can see that it's putting together a bundle to the to deploy, sets it all up, and here's my final job, all the aspects of it, how much code there is, how it all works, the cost and everything. And so it's just going to be a straightforward API to do that. I don't have more details than that though.
Awesome, that helps. Then we had one last question from Rick. What's the timeline for the IDE in the cloud?
We're hoping this fall. So within a few months, we'll see how that goes. But that is, high on our priority list, and partly for training purposes as well. We want to start using this for our trainings at Julia Computing, to make sure that everyone's able to spin up, and particularly on parallel computing trainings, right? We want to be able to give access to GPU machines, and allow folks to work with GPU programming and get things going. So that's kind of the goal, is to get things going as quickly as possible. But yes, hopefully, by November we'll see something along those lines.
Awesome. Well, if there aren't any further questions, we certainly appreciate everyone's time, and thank you, Matt, for the presentation today. Just a comment here, just saying thank you. So thank you all so much for your time. We appreciate it. Feel free to visit us and ask us questions. We're more than happy to help in any way we possibly can. So thank you so much.